Right, Assalamualaikum and good evening. My name is ZAKI, and me and my friends are going to present about the data structure of Spotify. First of all, I'm going to introduce my group members. First of all is AMIR KEIZRUL bin MUDZIR, and then Alif Haiqal bin SHARUN, and lastly AHMAD AFIF HADI bin RAHIM. Alright, first of all, Spotify. What is Spotify? Okay, Spotify is a leading music streaming platform that offers users access to millions of songs, albums, playlists, and podcasts. Users can discover new music and create personalized playlists, follow their favorite artists, and enjoy a seamless listening experience across various devices. Meanwhile, the Spotify operation, the first operation is finding music. The user can browse Spotify's library by genre artist, album, or even curated playlists made by Spotify staff or other users. And then playing music. On demand, once you find a song or podcast, you can simply hit play to start listening. In playlist, you can create your own playlist or listen to playlists made by others. Playlist a great way to group together songs that you like and listen to them in specific order. Okay, then and then cue music. When playing music, you can cue the next song to the so the Spotify will play the next song that you have in queue. All right, next
Okay,
Spotify operation, I'm going to pass to Ahmad Afif.
so for the Spotify operation, there is four algorithm in data structure that Spotify use. The first one in linked list, the second one is queue, the third one is binary search tree, and the last one is dynamic array. So the first one is queue data structure. Spotify might use a priority queue data structure to manage the order of songs in the queue based on factors like user preferences or release date. This ensures that the next song to be played is the one with higher priority according to the chosen criteria. Here's how the queue could be represented for Spotify playlists. So, songs are added to rear end of the queue. Songs are removed from the beginning of the queue. So you can see here from the front or head, it has been dequeued. So this follow the first in first out principle. So you can see the song is now playing is the first songs. So you can see here, this is the third song that has been dequeued. So there's the last song that it might have it should be in queue through the from the tail and Oreo part. So this structure ensures that songs are played in the order they were added to the playlist, maintaining the playlist sequential nature. When a song finishes playing, it is removed from the front of the queue and the next song in line becomes the new front of the queue ready to be played next. For the next one is linked list. Playlists are typically implemented as linked lists where each node represents a song. This allows for efficient insertion and deletion operations, which are common when users added or remove song from their playlist. So each node represents in the playlist the head point to the first song in the playlist, the tail point to the last song in the playlist. So each node contains two parts. The first part is song, example song title, artist, or duration. For the second part, a reference to the next note in the list. So means it point to for the second songs. So this structure allows for efficient insertion and deletion of songs in the playlist queue, as well as traversal from one song to the next during playback. Each note only needs to store a reference to the next note, making it easy to add or remove without the need to shift or resize the entire data structure. Next one, binary search tree. Organize songs. Binary search tree organize the songs in a playlist based on specific criteria, such as alphabetical order by songs title or chronological order by release date. Here's how BST or binary search tree might look. So each node represents a song in the playlist. The left child of node contains a song that comes before it's alphabetically. The right child of a node a song that comes after alphabetically. This organization allows for efficient searching of songs based off their titles. For example, root node representing a song which would be somewhere in the middle alphabetically. Second song and sixth songs represent song come before after song respectively. So you can continue the playback searching. So the searching for a song by its title can be done efficiently using property of BST. However, playlists are usually not organized such as this. So while it might be useful for certain types of searches or organizations within a playlist, it may not fully capture the complexity and dynamics of playlist management on platforms like Spotify. And lastly, for dynamic array, it also is also known as a resizable array. Is a data structure that allows element to be accessed using an index like a regular array, but it can dynamically resize itself to accommodate a varying number of elements. In the context of Spotify playlists, a dynamic array could be used to store the list of songs. So each element represent a song in the playlist. The array automatically resizes itself as songs added or removed, allowing for a flexible number of a song in the playlist. Element can be accessed efficiently using their index. So here, for the first part, you can see in original array before resize, you can see it loaded with many songs. So it seems like a full. So dynamic array automatically, if the Spotify use the dynamic array to adjust its size as needed to accommodate new song being added or existing songs being removed. This resizing ensures that the playlist can grow or shrink without needing to allocate a fixed amount of memory upfront or waste memory if the playlist size decreases. So dynamic array provide efficient to playlist song using their index, which simplifies operation such as adding, removing, or accessing songs in the playlist. However, dynamic arrays may require occasional resizing operations, which can be computationally expensive, especially if the playlist grows significantly in size. To mitigate this, most dynamic array implementations employ strategies to minimize the frequency of resizing operations, such as doubling the array size when it reaches capacity. That's all for me. I'm Ahmad Afif Abdul bin Rahim. I'm gonna pass the next point to my fellow friends.
Okay, so I'm Amir KEIZRUL bin MUDZIR, and I will be presenting about the running time. So the question 3 asks us to pick any one operation in question 2 and present the algorithm. So we choose the operation of queuing. So the operation, the firstly is enqueue, which is adding song to the queue. So the enqueue operation involves adding a song at the end of the queue using the offer method. Like we know just now, the queue algorithm will put the song that will be queued from the tail. Since this operation is in constant time, we represent it as O1. So the next operation is dequeue or play next song. The play next song operation involves one step, removing and returning the next song in the queue using the poll method. So since this operation executes in constant time, we represent it also as 0, 1. The third one is pick or view next song. The view next song operation involves one step, which is retrieving the next song in the queue without removing it using the pick method. Also, this operation executes in constant time, so we represent it as 0, 1. For the calculation, we sum up all the complexities of all operation. So the enqueue O1, the dequeue O1, and the pick O1. So the total will be 0 and 3. So next. So what can we conclude from the finding in 3.1? So the things that we can conclude is the runtime complexity of the algorithm used in Spotify code for queuing song is 0 and 1. This indicates that all operations including enqueuing, dequeuing, and picking at the song in the queue execute in constant time regardless of the number of songs in the queue. The algorithm demonstrates excellent efficiency for managing song queues in a music streaming application like Spotify, ensuring a seamless user experience. So next. So I will explain about the code. Okay. So the firstly we have the Spotify class, which is it is declared with a private instance variable song queue, which is the queue of a song. It is initialized as a new instance of linked list in the constructor. And then we have the constructor, which will initialize the song queue variable as empty queue implemented using a linked list. And then the enqueue method. Enqueue method adds a new song to the end of the queue. It takes a song object as a parameter and adds it into the song queue using the offer method, which adds the element to the end of the queue. It also will print a message indicating that the song has been queued. And then we have the dequeue method. The play next song method involves returns the next song in the queue. So if the queue is not empty, it will remove the first song from the queue using the poll method, which returns and removes the head of the queue. It will then print a message indicating that the song is now playing. So if the queue is empty, it will print a message indicate that the queue is empty. And then we have the pick method. The view next song method retrieve but does not remove the next song in the queue. If the queue is not empty, it retrieves the first song from it retrieves the first song at the head of the queue, and it will display the name of the title of the song. But if the queue is empty, it will print a message indicating that the queue is empty. And then we have the inner class, which it will represent the song. It is a private inner class within the Spotify class. It represents individual song and contain attributes for the song title and artist. It has a constructor. It has a constructor that initialize the song's title and artist, as well as getting methods to retrieve the title and artist of the song. Okay, so lastly, the main method. The main method is used to for the Spotify function to run. Basically, we'll call up the method and it will run. Okay, so we will go to the output. So as we can see here, when we queue a song, it will output as the song name, which is Shape of You, has been queued. And then we queue another song, which is Dance Monkey, has been queued. So the pick method, which is view next song, we will view what song is next. So next song in queue is Shape of You. And then the now playing, which is the DQ method, play that song. So since the queue there is a value in the queue, so it will show now playing the name of the song, which is Shape of You, and then after it has done playing, the next song, which is Dance Monkey. And then after that, since we only input 2 songs in the queue, so the queue is empty. So it will pop up a message that say please add songs to the queue. So that's it for me. I will pass it to my friend.
All right. I'm Haiqal bin SHARUN, and I will be presenting the conclusion. So what can we conclude from this research? We can conclude that queues are utilized in Spotify for managing song playback quick queues. Users can enqueue songs to create a playlist of songs played in a sequential order. Link list, playlists, or user libraries. Each node in the link list can represent a song, and user can perform operations like adding, removing, or reordering songs within playlists. Additionally, linked lists can be useful for representing user activity history, such as recently played song or browsing history. Also, trees could be employed in Spotify's backend for organizing music catalog data. The hierarchical tree structure may represent categories like genre, artist, album, and playlist. Furthermore, binary search trees or BST or balanced trees may be used for efficient searching and retrieval of songs or albums based on criteria like artist name, album title, or release year. Arrays can be used in Spotify for various purposes, such as storing audio data for streaming or catching frequently accessed information. For example, an array may store audio sample for a currently playing song to facilitate streaming, or it could be used to catch user preferences or metadata for quick access and improve performance. The strategic use of the data structures with the Spotify's architecture enhance the application's efficiency, scalability, and user experience. So that's all from us. Thank you for watching and listening to our research, spreadsheet data, and thank you for your patience. And that's all from us.
Bye bye.
Thank you.